to do a full example. Okay, we will do an example to analyze the shear stress, and the more important, the objective is to apply all the 5 rules, or all the 5 rules. So example number 1. So as I said, you have this image. Right. So for the beam and load shown, determine the section, or consider section NN. Determine the shearing stress at point A and also shearing stress at point B. What I'm going to do something further. We're going to form the equation of the distribution of the shear stress, and we are going to determine the Y max value. Okay. So the first thing we tend to ask ourselves, hey, this is a not so straightforward question. But before I go on, so I want you to know what we are seeing. So if I will draw my transformation, if I were to sketch my transformation, this is X and this is Y, rotation about Z. So what we have over here is a cross-sectional view. And then if we were to draw a transformation, this will be our Y, this will be our Z, this will be our rotation about X. Okay. So we know that, or not, we know we have to determine the shearing stress. And what we are going to find out is we're going to apply the formula that shear XY is equal to Vy over IZZ QZ over T. Okay, so we're going to apply that formula over there. Okay, so to make things quicker for us, okay, I'm not going to find the centroid and the second moment of area. I think you are very good at that. Okay, so given, or this is given, that the Y bar is 35 millimeters from the top, and the IZZ is equal to 5.8133 times 10 to the power minus 6 meter 4. Okay. So we know what's our IZZ, right? So the first thing we have to know, what we don't know. We don't know what is our QY. We don't know what is our QZ, depending on the point of interest. We also don't know what's our T. But we know that Vy is constant regardless of whatever we look at. Okay. So for this case, a lot of students, when they see this question, they say, okay, Vy is equal to 180 times 10 to the power 3. That's wrong. Okay. That is not Vy. Okay. So the best way to do this, okay, to determine Vy, okay, we have to construct the shear force diagram, or sometimes determine the shear force equation. Some situation you have to determine the shear force equation. Okay, so let's construct the shear force diagram. Before we go do that, we need to draw our free body diagram. Okay, we need to draw free body diagram. So this is our free body diagram. So we know that we have a point A. We know that point B, this is equal to AY. Over here, this is your BY. And then you have a load exactly at the center coming down. Is doing 180 times 10 to the power 3 Newton. Okay. So what we can do is, if I were to draw a vertical axis YY, okay, sorry about that. If I were to draw a different color vertical axis YY over here, right? We know that the structure, the left hand side and the right hand side are the same. Okay, so we know that this structure is axis symmetry in terms of geometry and load about the y-axis or about the y-axis. Okay, therefore AY is equal to what? Okay, I'll about the y-axis. Right, so therefore AY is equal to BY. So now when we do static analysis, right, when we do static analysis, some mention about forces in the y direction is equal to 0. We have AY plus by BY minus by 180 times 10 to the power 3 is equal to 0. So we know that AY is equal to BY, so we can write it 2AY is equal to 180 times 10 to the power 3. Okay, then finally, we know that AY is equal to 90 times 10 to the power 3 Newton. So when we construct our shear force diagram, what does it look like? Okay, so just to quickly recall how to construct our shear force diagram. So this is our V. This is positive 90 minus 90 times 10 to the power 3. This is our X distance. This is 0. This is our 0.5. I think it's 0.5. Am I right? Yep. And this is 1.0. And the units is in meters. So now when we construct, you can see why you cannot put V max is equal to 180. So it will go horizontal at 90. Then over here, it will drop by 180. Then it will go horizontal. And then from here, it will go back up to 0. Okay. So that is our shear force diagram, right? So one thing weird is, this is why the NN position along the x-axis, what is this value? It's not given, but it's not important. Why it's not important? Because if you take any distance, x distance here, or another distance over here, which is x, right? The shear force is still going to be what? 90. So that's why when they say, okay, guys, okay, the question asks, what is the considered section NN? The first thing you ask, where is NN? But after constructing the shear force diagram, we realize that it's not important at all, because from 0 to 0.5 meters, the V in the Y direction is 90, constant. Okay, so from here, we realize that we know that what is our V max, which is equal to our Vy. This will be equal to 90 times 10 to the power 3 Newton. A lot of times throughout my years of teaching, students look at 180. Okay, I'm going to put in 180. Don't do that, okay? You just shoot yourself in the foot. Okay, it's not equal to 180. Right. So now, coming back to the equation over here, right? We know our Vy, we know our Izz, which we apply the rule, it's constant regardless of point of interest. Okay, so we have those two values. So now we can seriously look at the shear stress at point A. Okay, so now we are going to find, let me get this diagram over here. Okay, so we want to find the shear XY at point A, right? So now you guys have the impression, right? So we know that we have a centroid position. Okay, we are aware that you have a centroid position. I'm just sketching this. Okay. So this is our centroid position, and the centroid position, this distance over here, given to us, okay, is 35 millimeters. If it's not given, it's easy to determine, right? So now we have to find our first moment of area, right? So this is about ZZ axis. So we want to find QZ, which is equal to width, depth, y bar. Okay, with that y bar. So we know that the width, if you want to work in millimeters first, you can. The width is 160. The depth is 20. The y bar is 35 minus, right? 35 minus by 20 divided by 2. Okay, some of you will be a bit confused, but don't be. Why is that? Because we know at the distance, the section or the area or the defined area interest, the center is here, and the distance from here to here is what? 20 divided by 2. And to find our distance, wait, I'll use a different color to find a distance over here, which is our y bar is equal to 35 minus by 20 divided by 2. Exactly like what you see. So from here, we have 35 minus 20 divided by 2. Wait, 20 divided by 2, 35 minus times by 20 times 160 is equal to 80 times 10 to power of 3 millimeter cube, or 80 times 10 to power minus 6 meter cube. So we have our QZ already. So from here, we can directly